Today, I want to talk a little bit about a whole different way to represent and define and imagine derivatives. And we're going to see it's going to take us on a pretty cool story. Here, I just showed all the little things I was working with in Desmos to kind of understand it a bit more. And it's just a cool thing to see actually how cool math can get if you just think about, a topic a bit more deeply. And basically, what we're going to talk about is what I want to say is that we can represent or define the derivative as the unique slope which makes the normalized error vanish. So first of all, before I explain what that means, how do we even normally think about a derivative? Well, we have a function and then we choose 2 points in that function and we can call one point x0, and then this point obviously will be f of x0, the value of our function at x0, and then we can choose a free variable and we're going to call it x, and this is obviously going to be f of x, and then we draw a line going between these 2 points, a straight line going between these 2 points. And then as x gets closer and closer to x0, f of x will get closer and closer to f of x0. And then if we keep on drawing a line between these 2 points, eventually, when x gets, very close to x0, these 2 points will basically be the same point, and we're just going to get the tangent. I'm going to draw it here in highlighter. Our line will just be basically the tangent to our function at the point x0, and the slope of this line, well, that's nothing else than the derivative of our function at the point x0. And to get the slope between 2 points, we just do y2 minus y1 over x2 minus x1. So basically, this is the same thing as saying we're taking the limit as x goes to x0 of f of x minus f of x0, y2 minus y1 over x2 minus x1 or x minus x0. This is how we normally define the derivative of a function, at the point x0. And there's nothing wrong with this, but this is kind of a definition that we use for only when we're talking about 2D functions. When we're talking about functions, in the 2D plane. As soon as we look into, when we go to multivariable calculus, and we look at higher variable functions, when we look at multivariable functions, then this definition doesn't really work anymore, and it's not really used anymore. And there's another better definition in terms of errors of a function, and that's where we get the idea that the derivative will just be the slope, or the value, in higher order functions is going to be the matrix, the Jacobian matrix, which makes the normalized error vanish. What do I mean by that? Well, first of all, let's first get like a little intuition. Let's just imagine we have our function x squared here, and let's imagine we want to approximate this function x squared with a linear function. I'm going to call this function lm of x. This is going to be our linear approximation to our function x squared at a point a. Here, let's say we want to approximate this at this point. Let's say, a equals 1.5 or equals 2. We want to approximate this function at this point. Well, we can create a straight line function, which is going to be f of a plus mx minus a, and this is basically just the same form as saying a straight line y equals mx plus b, because again, what is b? B will just be when we evaluate our function at a point, let's say a, f of a equals m of a plus b, so then b would just be f of a minus m of a. And again, if I spell this function out, this will just be f of a plus mx minus ma. And again, fa minus ma, this will just be our value b, so we're going to get mx plus b. This is kind of the classic equation of a straight line. And this will be our linear approximation of a function, where a, this is just the value of a function at the point, x is the variable that's going to be approaching a, and this is something we can choose. This is a free variable. And now, if I plot this over here, we have a little approximation. This straight line at the point a will approximate our function, and we can choose this line differently. If we change m, this line will kind of approximate our function differently at the point a, which is 1.9 here. I can make it 2. Now, how can we choose the best line? How can we choose the line that will approximate this point the best? Well, we got to introduce something called the error function, or the remainder function, Rm of x, and this will just be our function f of x minus our approximation, minus our linear approximation, lm of x. So, if I spell this out, this will just be f of x minus the linear approximation we made for this function at this point, which is going to be f of a plus mx minus a. This will be our remainder function, and this function will basically give us the distance between our function that we're interested in and our approximation. This distance will be here, and then it's the straight line distance between them, and it's going to get smaller and smaller and smaller and smaller. And again, I can plot this error function here, and we can see that at the point x equals a that we're interested in, our function goes to 0. Our error function will always go to 0, no matter what m we can choose, because obviously m is the variable that we can alter. But no matter what m we choose, our error function will always go to 0. And that makes sense because we have a straight line which crosses our function at the point 0. So eventually these two values have to be the same. What we want though is this isn't enough for us. We want the best possible approximation. So we want the straight line function which approaches our point here f of a as fast as possible. We want the best possible linear approximation to our function at the point a. So how do we decide which approximation is the best? Because we can see here our error function goes to 0 pretty quickly. Our lines here get smaller and smaller and smaller. Well, what we need to introduce is the normalized error. And the normalized error would just be our error function over this value x minus a. And what is this value x minus a? Well, this is just kind of a base. This is going to be our base kind of value that we're working with, because again, if we have a function and we want to approximate this function at the point a, let's say we have a value x, and let's just imagine x approaches a, normally, like in a linear fashion. Well, then, this is kind of our baseline approach. We want to create a line which, as x approaches this value a, approaches this value faster. So kind of our baseline approximation, as x approaches a, well, obviously, this is going to go to 0. As x approaches a, x minus a will go to 0. But we want our remainder function, which goes to 0 much, much, much faster than that. Which means when we take the limit as x goes to a, I want this quotient to be equal to 0. And what I'm saying is that there's only one solution. There's only one such linear approximation function, which, when compared with our base value x minus a, takes this quotient to 0. And this is kind of a crazy thing to think about, because both of these things go to 0. So 0 over 0 is kind of undefined, or if they both go to 0, then the value should just be 1 because we're dividing by the same thing. But no, our error function goes to 0. Again, if I plot our value x minus a, they both are going to 0. X minus a, which is here, is going to 0. Our error function is going to 0. But our error function is going to 0 so much faster that if I take their quotient, a will equal to 0. For example, if a is 2, let's say if a is 2, and then let's say x equals 1.9. Well, then maybe our rm of x, let's say our rm of x, our error function is, let's say, going to be 0.0001. We are that off from the actual function. So if we actually look at the value here, we can imagine that as x gets very close, we can see in green is our approximation, and we can see that it's very close to the actual function. We can barely see a difference. And then let's imagine x minus a. Well, the value of x minus a, if x is 1.9, it's just going to be 0.1. It's going to be negative, but just imagine I flip it. So then, again, if I just multiply this by 100 or 1,000, to make this into normal numbers, this is like saying I have 1 over 1 million or 1 billion. And eventually, this will be a very small value. So as I get closer and closer to a, this fraction goes to 0. But it goes to 0 only in one case. It goes to 0 only if our chosen value m is in fact the derivative of our function at the point a. So there's only one such linear approximation which makes our normalized error go to 0, and that linear approximation is such that our value m equals the derivative of our function at that point. For any other value of m, again, look, let's zoom into here. If this is our error function in red, if I choose a different error function, which I have over here, so this is our function when a equals 2. This purple thing is our perfect error function where m equals a derivative, and this function in red is going to be our error function when m does not equal the derivative of x squared. So when m does not equal 2. And again, we can see this is the green line over here. If our tangent line, if our line is not perfectly tangent, if we choose a different m, our error function is going to go to 0, and it will still go to 0 much faster than this green line over here, but our perfect approximation will go to 0 much, much, much faster than this red line. Again, if I keep on zooming in, our approximation is basically at 0, while this approximation is still not at 0, even though it's better than our green approximation. So what I'm trying to say is that there's only one such linear approximation which makes this true. For any other thing, if m does not equal the derivative of f of a, I'll get a value which is a constant, for example 1 or 2, and this just means that our remainder function is smaller of this function, which means it goes to 0, but it is always it basically goes to 0 bounded by constant of this function. So it doesn't go to 0 infinitely faster, but it falls. It is bounded by a constant of how fast it goes to 0. It's kind of a bad explanation, but it basically doesn't go to 0 much faster than this. It only goes to 0 a little bit faster. So this is how we actually define the derivative also in higher dimensions. It's kind of the value which gives us the best linear approximation to our function. And again, let's just try to apply this for an example. Let's say I take our function x squared. Well, then our remainder function will just be our function x squared minus our approximation, which is going to be f of a, and f of a in this case will be x squared, a squared minus m x minus a. And then I divide this by our base value, x minus a, and I take the limit as x approaches a. Well, what is x squared minus a squared? That's just the same thing as x minus a, x plus a. So basically, if I write this down again, I'll get x minus a, x plus a, there's a plus here, minus m x minus a over x minus a. And basically, what I will get at the end, this cancels, this cancels, this cancels. I'll get the limit as x approaches a of x plus a minus m. When x approaches a, this will obviously be 2a minus m. This is our limit. And this limit will equal 0 only if m equals 2a, which in fact is the derivative of the function x squared. The derivative of x squared is 2x, and at the point a, this derivative just evaluates to 2a. So this is our value m. This is just another way to find the derivative of a function. And ultimately, if you rearrange the variables, it is just the same thing of this, but we're using a different lens to kind of we're using a different kind of thought process to get to the derivative. And in higher dimensions, this is specifically what you think about, because when you have higher dimensions, you can't just think of 2 points and the slope between 2 points getting closer and closer. In multiple dimensions, you can't really think of that, but you can think of an error function. You can't think of a multi-dimensional line which points to our value, which gives us a direction of our value, which is the fastest possible way to actually get to our value. So it's kind of the vector which will give us which will make us come to our value f of a as fast as possible. This is kind of how you think in terms of errors. It's how you actually think about a derivative in multivariable calculus also. And I just think it's very clean. It's a completely different picture of the derivative. It doesn't even seem related, but it still gives you the derivative. We have our error function here, and we want to choose an error function such that it goes to 0 infinitely faster than our baseline function goes to 0. And I think it's pretty cool. I think it's a pretty interesting example. And then again, most people might just see that, well, this a linear term that we're looking at, this is just the first order Taylor expansion of any function. We could also look at higher order approximations, and again, this is what I've done here. We have a little function e to the x, and then we can take our error function, which is this. We're using the first order Taylor expansion. So this is f of a plus the derivative of f of a, x minus a, and then we can take the second order Taylor expansion and we can make the error function out of it. And we'll see that this error function goes to 0 even faster than a linear error function. But this, this will already give us the first and the second derivative. The derivative is defined as the error function, the linear approximation error function, which is gonna go to 0 as fast as possible. There are other functions which go to 0 even faster, but they won't be linear approximations anymore. They'll be quadratic or cubic approximations. The derivative is only defined as the unique slope, which makes the normalized error vanish, and the normalized error we're talking about is we obtain it from a linear approximation. So yeah, I hope this kind of gives people a deeper intuition about derivatives. It's kind of a video all over the place. I just kind of wanted to mention this because it's pretty cool, and it's more useful in multivariable calculus. You actually learn that whenever you look at the derivative, you just want to solve the limit as x approaches a. You just want to say that this limit of f of x minus f of a minus mx minus a over x minus a, you want to find an m, which can also be a matrix, which makes this limit go to 0. And this is how you define a derivative. If there exists such an m that this limit equals 0, then you can say that there also exists a derivative of this function f of x at the point a, and the derivative will precisely be this value m. So yeah, thank you for watching. I hope it made sense, and see you next time.